Hello world, this is Craig. Today our goal is to start a series of about 5 videos to learn 8008 assembly language. Assembly is one of the lowest level languages, second only to the machine code. And by low level, what we mean are languages that are very intimately tied to the processor itself, versus high level, which are languages that we run on a system and we may know nothing about the processor. And the high level language will have a lot of very high and complex capabilities and functions, like square root or the trig functions or inverting a matrix. That kind of thing can be a single command in a high level language, where in a low level language we are really, really intimate with the processor and we're pushing things around. So if you're thinking of wanting a language that's more like three-dimensional chess, assembly language is not for you. Assembly language is much closer to those little sliding puzzle things where you just push things around. And in assembly, you will literally be pushing values around in little areas ad nauseum, it seems, at times. So the high-level languages like Fortran or C or C++ or the new ones, Python, whatever they're playing with now, this is the opposite. This is the lowest of the low-level languages. And what we're going to do today is we're actually going to start with the machine language. And then eventually we will go over into the assembly language and learn the mnemonics. And we're going to do all old mnemonics in this series. Okay, there's 3 core fundamental concepts that we're going to learn when we're talking about assembly. The first is registers. The next is memory. And the third is flags or conditions. Okay, those are the 3 things that are going to be critical to understand in understanding assembly. And everything we learn in the 8008, we're going to be able to drag right up into the 8080 and the 8085, or even backwards down to the 4004 or the 4040. So we're not wasting time here. We're just learning on a very simple, classic, very historically important processor. Okay, so let's look at registers. The 8008 has got 7 general purpose registers, and these are registers that we will use as the user, as the programmer, and they're all 8-bit registers, and we'll look at them in the next sheet what their names are, but we have 7 general purpose registers that we can use. The 8080 or the 8008 itself has 9 additional registers that only it can use. And we can't really directly control any of these registers. There are 7 registers that are for the stack. These are 14-bit registers, and we'll talk a little later as to what the stack is. There's a video I have earlier about the 8080, 8085 stack. It's quite a bit different in the 8008. So for right now, we're going to leave this for later and just say there's 7 registers that are the stack. There's 1 register, it's again a 14-bit register, that is the program counter. This is basically a bookmark for our program saying that this is the instruction that we're about to execute. And then we have 1 register that is our stack pointer, and that's a little 3-bit register. We have something that's kind of between a register and something else, and that's we have 1 memory location that is user accessible. So in all of these commands, there's only 1 way that we can put something into memory or take something out of memory. These are our 7 general purpose registers. They're simply called A, B, C, D, E, and H, and L. These are all 1-byte registers, so they have 8 bits, and all of the instructions that we will be using will be just moving things around these registers, subtracting 1 register from another register, putting information into a register, doing logical things between registers, and that kind of thing. They're all very, very basic. We then have this other thing that's kind of a hybrid. It's not really a register, but we treat it like a register, and that's our 1 accessible memory location. And we can control what our memory location is that we're pointing to, but once we control it and we're pointing to a certain memory location, we can just access that like another register. Each of the registers have a number associated with them. So the register A is 0, B is 1, 2, 3, 4, 5, 6, and then the memory is register 7. later on when we're writing in an assembler, we can either refer to a register by its letter, or we can, in most assemblers, refer to the register by its number. But when we're doing machine code, we will only refer to register by its numbers because, of course, the processor doesn't understand any letters. Okay, we'll come back to registers, but right now let's go on and talk about memory. Two important concepts with memory. Memory can be read-only, and our EEPROM is, an example. These are all read-only memories. We go out and we program them somewhere, and then once we program it, we can only read it. We also have random access memory that we can read-write. And so here's our random access memory in our mill mod system. So these little chips, we can either write a value to that and it will remember it, or we can read the value back and it'll give us the value that was last written in there. If we didn't write a value before, it would just give us junk back. But basically, this is our random access memory. We can write to a PROM. If we just have a PROM installed in this system and we write to it, we can write. It's not going to burn anything up. But when we read that memory location back, we're not going to get the value we just put there. We're going to get the value that was there when this thing was programmed. Okay, the second thing to remember is not all memory is there. So, for example, when we have our memory put into our system, this is the way we kind of have it laid out. We have a section of memory that is our ROM. This is our program memory, and so the program will start in this memory location, goes up 256 bytes over into this one, and then it goes to that one, to that one, to that one, to that one, so forth. So if we look at our memory starting at 0000 and going all the way up, it sequences through these chips. We then come over to this card, which is the next in sequence, and we can read that one, we read that one, but these guys are gone. There's nothing there. So if we try to read memory from these locations, we will just get some arbitrary junk. We may get a 0000 or we may get a FFFF. Who knows what we're going to get because there's nothing there. We're just going to get junk. And then there may be a gap. Who knows where we decide to put this memory. There may be a gap, and then we have our RAM. And of course, we could have additional cards in the system. We can have up to 4 cards in our mill mod system. And so we may have some contiguous memory. We may then have a gap. We may have RAM. We may have ROM. We could swap these things around so that it goes like this. We've got our ROM, and then we've got RAM, and then we've got more ROM, and then more RAM. This is all up to how we initially configure the system. And as the programmer, we have to keep track of where this memory is. But basically, the memory is going to be, for the 8008, a 14-bit value. And we are generally going to have that memory start at 0000 in decimal or in hex, and it's going to go up in little bits or little blocks to the maximum value. And of course, with a 14-bit value, the maximum value we could have would be 3FFF if we're talking about in hex. So our memory is going anywhere between 0000 and 16383 in decimal, or 0000 hex to 3FFF in hex, or 000000 in octal, up through 37777, or in split octal, 000 up through split octal will be 077377. So these are going to be all of our memory addresses, and these are just bytes. So each of these memory addresses are just a 16-bit, or just an 8-bit byte. And so this is memory address 0000. This is 0001, 0002 in hex, all the way up to the last memory location that would be 3FFF in hex, or 077377 in split octal. So these are just sequential memory locations. They may have a program in it. They may have a program and data in it. They may just have data, or up in some location, they may be RAM, where we're just using them for either parts of our program, or we're putting data in there. Who knows what we're using it for in RAM. This is where it becomes accessible to us as the programmer to read and write and put storage, use it for storage. Okay, so that's our memory. And let's now look at a few machine instructions. This is where we're going to start. We're not going to do a lot of stuff with machine instructions, but we're going to do only machine instructions today, and we will actually get with back to the assembler in the next video. Okay, machine instruction by definition is in binary because the binary is the only thing that the microprocessor is going to understand. So all machine instructions are in binary, and they come in little groups. And for example, the first thing that we're going to do is the load machine instruction. Load machine instruction is going to start with the value 1, 1 in binary, and then it's going to say what is our destination register, and then which is our source register. So for example, if we want to load register B, if we want to load register A from register B, it's going to look like this. It's going to be a 1, 1. Register A is the destination, which is 0, 0, 0. Remember from our little chart over here, register A is 0, 0, 0, register B is 0, 0, 1. From 0, 0, 1. So this instruction is going to be 3, 0, 1 in hex. Okay, so that's load register A with whatever was in register B. So that's going to take the 8-bit value that's in register B, make a copy of it, and put it into register A. Just duplicate B into A. Okay, and that's about the complexity of our machine instructions. We're not doing anything more sophisticated than dinking with these registers, a bit at a time. So another example would be, let's say we want to load H from A. So we want to take whatever is in A and put it in H. So that is going to be the 1, 1 again. H, if we look at this, is 1, 0, 1. And A is 0, 0, 0. Okay, so this is going to be 3, 5, 0. Now we can load A from our memory location. Remember we said we got this memory location here that we can load from, and we'll talk about later how we figure out what memory location we're loading from, but for right now we can load from that memory location. That's going to be 1, 1. The destination is 0, 0, 0, that's A, and the source is going to be the memory location, which from our little chart here is 7, 1, 1, 1. 1, 1, 1. So 3, 0, 7. If we feed that to the processor, 3, 0, 7, it's going to take whatever's in our memory location and put that in register A. Okay, those are all the load instructions. Now let's look at a different type of load that is an immediate load. And what this means is load the register from the next byte in memory. Okay, so whatever our instruction is at, so let's say that this is the byte of instruction that has, or this is the byte in memory that has our instruction in it, the next byte right here is going to have a little piece of data. And so what this instruction, the load immediate does, is it say take the whatever's in the next byte and put it into that register. And a load immediate, it looks like a 0, 0, and then the destination, and then a 1, 1, 0. Okay, so if we load A from the immediate data, that's going to look like 0, 0. A is 0, 0, 0, and 1, 1, 0 is our immediate. And so this is going to look like 0, 0, 6 Q. So in our instruction, or in our memory, we will have a 0, 0, 6, and then let's say our next one is 3, 2, 2. What that will do is it'll do this instruction, which says take the next byte and put that in register A. So this will take the 3, 2, 2 and put that in register A. So after we've completed that instruction, register A has the value 3, 2, 2 in it. Probably the next simplest thing is our increment register. And so an increment is going to be a 0, 0, register, 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 0, 0, 0. Okay, and I'll give you a heads up that the decrement is going to be a 0, 0, register, 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 0, 0, 1. That's going to be the decrement. So let's say we want increment register B. That's going to be a 0, 0. B is 0, 0, 1, 0, 0, 0. Okay, so we have a 0, 1, 0 is a increment B. Okay, if we wanted to increment H, that would be a 0, 0. H is a 1, 0, 1, 0, 0, 0. So that's going to be a 0, 5, 0 is increment H. Now, one thing we can't do is if we try to do an increment A, believe it or not, of all things that are missing, increment A is not a valid instruction. That would be a 0, 0, 0, 0, 0, 0, 0, 0, or 0, 0, 0 in hex, and that's actually a halt instruction. So if we tried to do an increment A, it would just bring the processor to a halt, and no further instructions would get executed until it underwent some kind of a reset. So that's common with machine language. There might be an instruction that either doesn't do what you think it's going to do, it's going to do something completely different, or it's not a valid instruction at all. We know what the decrement is. Let's do a decrement B. Decrement B is going to be a 0, 0, 0, 0, 1, 0, 0, 1, or 0, 1, 1, Q. That's going to decrement B. We could decrement H. That'd be a 0, 0, 1, 0, 1, 0, 0, 1. Okay, so 0, 5, 1 Q would decrement the H register. There is still no decrement A. If we try to decrement A, that's 0, 0, 1 Q. This is actually no instruction. So there is no instruction 0, 0, 1. Who know? I don't know what the processor would actually do if it got a 0, 0, 1. We'll have to try that sometime. Okay, the last one we're going to do today, and probably the last one that we'll do in machine language before we just switch over to assembly next time, are the logicals. Of course, with the logicals, we can AND, we can OR we can exclusive OR. That's pretty much what we're limited to with 8008, these three logicals. In all cases, we're going to be doing this with another register or immediate data, and the answer is going to go into the A register. So an AND instruction means AND A with a register and put the answer into A, or AND A with immediate data and put the answer into A. So let's look at just register to register, and if we're going to AND with anything, its generic pattern is going to be 1, 0, 1, 0, 0. So this is the AND, the 1, 0, 0. Register, register, register. So an AND A with B would be 1, 0, 1, 0, 0. That's our AND A. And with B, it's going to be 0, 0, 1. Okay, so 2, 4, 1 is AND A with B. And put that in as a AND. So kind of think of a little A, and A with B is going to be this value right here. Or, so if we're going to OR A with a register and put the answer in A, an OR is going to be a 1, 0, 1, 1, 0. So this is an AND, that's an OR. Register, register, register. So if we're going to do the same thing, if we're going to OR A with B, so we're going to OR A, the A is implied, with B, because A is the only thing that we can register with, then that's going to be a 1, 0, 1, 1, 0, 0, 0, 1, or 2, 4, 2, 6, 1 is going to be OR A with B. And exclusive OR, if we are going to exclusive OR, it's going to be a 1 0 1 0 1, register, register, register. So exclusive OR A with B is going to be 1 0 1 0 1, and B is 0 0 1. Okay, so 2 5 1 is going to be exclusive OR register A with register B. So we would exclusive OR with B, just for shorthand. All right, well, that's all we're going to do with the machine instructions, and because you get the idea with this, and you can tell that this would be a very annoying way to program microprocessors. And we're going to switch over and start talking about the assembly and the format and the mnemonics next time. Okay, well, that's it for this video. If you have any questions, let me know. But I appreciate you watching, and I hope you found it interesting. Bye-bye.